Hi everyone, and welcome to my virtual thesis defense. I'm Mareesh Kumar Issar, and today I'll be presenting my work E-ASSOC, Enhanced Energy Efficient User Association Algorithm for Future Cellular Network. This work has been done under the supervision of Professor Ray Chaudhary, and my committee members are Professor Roy Yates and Professor Fedra Passager. So, moving on. So here is a brief outline of my presentation. I'll be going around starting with motivation, then present some background, then I'll formulate my problem statement. Then in order to solve that problem statement, I'll present the system model that I have been using along with the user association algorithms. I'll evaluate 3 existing user association algorithm and then present my own user association algorithm E-ASSOC, and then I'll present the evaluation results followed by conclusion and future. Okay. So in this slide, you can see a graph which shows on x-axis the year and y-axis is the global mobile data traffic in exabytes per month. So this graph has been taken from Ericsson Mobility Report of November 2019. And according to that same report, Ericsson states that by 2025, 5G networks will carry about 45% of world's mobile data traffic and will have around 2.6 billion subscriptions covering up to 65% of the world's population. Also, according to a report published in 2015, we can see that the total annual operational energy consumption of the telecommunication network was estimated to be around 242 terawatts per hour. And this also includes the operational carbon emission from these networks, which was around 169 million tons of CO2. Sorry for the mistake here, it's CO2. And this report also showed that between 2010 and 2015, the energy consumption of the network grew by around 31% from the level of 185 terawatts per hour. So from the graph on the left side, we can see that the demand for data is going to increase in the subsequent years. So we need to prepare the future cellular networks so that they can handle these demands. And also from the figures and the values on the right side, we find that these networks should also be energy efficient so that they don't consume much energy and lead to less CO2 emissions. So moving on. Here is some background regarding user association algorithms in general. So we'll first start by understanding what is user association. So user association is a mechanism by which a user is associated to a cell tower or a base station before the data transmission commences. And on the right, you can see a taxonomy of the user association algorithms. So in general, the user association algorithms can be classified into various types depending upon metric, scope, model, control, and topology. In the figure, I have highlighted specific section in these subsections in order to highlight the issues and the areas that we'll be tackling in this work. Also, for future cellular networks, there is a requirement for high amount of data traffic support, reduce energy consumption, and improving the quality of service for the user. And in order to achieve these targets, a prominent technology that comes up a lot of time is heterogeneous network. Now, moving on, I'll try to explain what are heterogeneous networks. So on the figure on the right side, you can see an heterogeneous network. A heterogeneous network comprises of basically a large cell tower called macro E node B or evolved node B in terms of LTE, and smaller cell towers called pico or home E node B. So the main purpose of using small cells is to address the issue of coverage gap and traffic hotspot. Coverage gap meaning some areas might not receive the signal, and traffic hotspots means locations such as fully packed stadium. So in those cases, small cells help in providing connection to a large number of people at a small spot. On the left, you can see I have highlighted the transmission power of a macro base station as well as the lower power loads. You can see the drastic difference in the transmission power of a macro base station in comparison to a lower power node. Also, the femto nodes, which are usually placed indoors, they can be further classified as open, closed, or hybrid, depending upon the access they provide to the users. So moving on, here is the problem statement which I want to tackle in this work. The problem statement is to design a centralized user association scheme for heterogeneous network in order to maximize the energy efficiency. Here, I would like to mention the definition of energy efficiency as well. The energy efficiency can be defined as the system throughput divided by the system energy consumption. So in order to understand this, we can think of it as follows. For example, if this is our system depicted in the figure, and if the system throughput increases, then the energy efficiency metric would increase. Whereas if the system energy consumption decreases, then also the energy efficiency term would increase. Here is a depiction of the system model. I have a macro base station or a central tower which has a large coverage radius depicted by the large circle, large blue circle, and there is a centralized controller which is attached to the macro base station. Also, there are 4 small cells located inside the coverage area of the macro cell, but they are transmitting at a different frequency from the macro cell. And there are few control signals, for example, uplink control signal and downlink control signal. So moving on to the system model part of this work, I'll start the system model part of this work by depicting some of the assumptions that I have taken. For example, here I have highlighted the key assumptions which I have taken for this work. I'm considering only downlink scenario, and also the users are not mobile, they are static, and perfect channel conditions have been assumed. A user can attach only to one base station, and all the base stations transmit at their maximum transmit power. Also, the macro base station cannot be overloaded, which means that all the users present in my system are capable of being supported by the macro base station. This is an important assumption. I'll come back to it in my subsequent slides. So moving on, this is the network topology of the system model. Here you can see there's a red triangle in the center and the coverage radius depicted by a red circle. So the triangle here depicts the base station, and a triangle with number 1 is the macro base station, which has the large coverage radius of 500 meters. I have also deployed 4 small cells or pico base station in the same topology at a distance of r over 1.414 in order to show the heterogeneous network, which has both the macro base station as well as the pico base station. Now, moving on. Here is the SNR calculation algorithm for the system model that I have used. In this algorithm, I have 2 statements regarding the calculation of SNR. The first statement here calculates the SNR for the user that is attached for the user and the macro base station. And the second SNR equation here calculates the SNR between the user and the pico base station. And we can see that these 2 equations are different by the terms that are highlighted in colors. For example, here you can see a yellow box representing the transmit power of the macro base station, whereas there is this yellow box denoted by P_SC is the transmit power of the small cell. The green boxes show the path loss model for the macro and macro base station and user, and this green box shows the path loss model between the pico base station and the user. And the other parameters are also used in this equation, and I'll go on in my further slides and explain what are the values of these parameters. So moving on, here are the simulation parameters that I have used for my system model. I've used 60 users, and I am simulating 200 iterations with 1 macro base station and 4 pico base stations, as shown in the topology slide before. The macro base station is having a coverage radius of 500 meters. And here you can see that I am segregating the macro base station and the pico base station in terms of the transmit power. The macro base station has a higher transmit power than the pico base station. Also, the bandwidth of the macro and pico base station are different, and the internal model for both of them is isotropic. Moving on. Here are the simulation parameters for the system model, which includes the path loss model, The part loss model for both macro and pico has been taken from 3GPP specification 36.814 mentioned in the reference below. And the shadow fading parameters are also mentioned here in the table. Another thing to note from this table is that the carrier frequency of the macro and pico cells are different, which means that there is no interference. Also, I have introduced a new factor here known as the macro pico load factor. Now I'll explain what this factor means. So this factor is nothing but the ratio of maximum load capacity of the macro base station divided by the maximum load capacity of the pico base station. And here I have considered that factor to be 5. So in order to make this example concrete, let's go back one slide. And we can see here I have 60 users. So if the macro pico load factor is 5, then this means that the macro base station can support all the users, because that's one of the assumptions. And the macro pico load factor will divide the 60 by 5 and we'll get a value of 12, which means that each pico or small cell can have a maximum capacity of 12 users. So now moving on. Now I'll be transitioning to the third part of this work, which is related to the user association algorithms. And to start, I'll present a baseline user association algorithm, or the max-SNR association algorithm. Here, SNR stands for signal to noise ratio.
Mareesh.
Yeah, Professor.
So how did you decide on the shadowing coefficient for both of those pico and macro?
Professor, I took those values from the 3GPP specs.
Mm-hmm. And do they have it for both macro and pico?
Yeah, Professor.
Mm-hmm. Yeah.
Yeah, so they might they also have like a different shadowing model, but I have used log normal shadowing.
Mm-hmm. Yeah, because you would expect that, because of different, like, in larger cells, you would expect more shadowing than in smaller cells, I would say. But
okay, but since like
I'm
I
just curious.
haven't
Yeah.
considered any obstacles as well here.
Mm-hmm. Mm-hmm. Okay,
So
thank you.
yeah, sure.
Mm-hmm.
So yeah, so here I'll try to explain the baseline or the max SNR base association algorithm. So in this algorithm, what we do is we check whether each user and a base station pairs SNR is the best SNR for that user. If it is so, then we check if the load at the base station is less than the maximum load capacity of the base station. If both these conditions are valid, then I attach the user to the corresponding base station. If one of these conditions is not valid, then the user will be automatically by default attached to the macro base station. So this is the baseline algorithm. Now moving on, I'll further suggest some of the improvements that have been studied in the existing literature over this association algorithm. So our first improvement is in terms of load balancing. So here we first need to analyze what these figures mean. So the figure to your left, which I'm pointing to currently, is the association, which is also the max SINR association. Here, the red dot of my pointer is pointing to the base station, which is the macro base station, and it has a larger coverage radius. The blue lines here depict the connection between a user and the macro base station. Here you can see that there are a lot of numbers of blue line as compared to green or red. Green and red denote the small cells, which are also depicted in the figure using different tiers. So tier 1 is the macro base station and tier 2 and 3 are the small cells. So here, one problem which we can observe is that the users which are very far from the macro base station are still connected to the macro base station, even if there is a small cell nearby. This happens because the users are still receiving a stronger signal from the macro base station. But the key point to note here is that the bandwidth at the macro base station as well as the other base stations is fixed. So if I attach more users to the same cell, then the bandwidth would be divided amongst more users, which means that each user will not get a sufficient amount of data. So in order to mitigate this issue, the authors have proposed a load balancing scheme in which they show the result as depicted in the figure on the right hand side. Now here we can see that the number of users attached to the macro cell, the blue lines are reduced a lot. And also the green lines and the red lines have increased. This means that the previously underutilized small cells are now being utilized as the users closer to them are attached to the nearby pico cells or the small cells. And also the another benefit is that the macro cell, since it has less number of users, the bandwidth can now be divided much more, which means that each user who is now connected to a macro will get an increase in the data rate. So the conclusion from this slide is that the load-aware scheme leads to more efficient resource utilization by shifting of load to underutilized small base stations. So moving on, here is the formulation for the load balancing scheme in terms of a convex optimization problem. Here we can see that the objective function which we are trying to maximize with respect to x, here x denotes the user association matrix, and what we are trying to do is maximize the throughput product with the association matrix. But here we are not just maximizing the sum of the throughput, we are maximizing the sum of the log of the throughput. So this log operator has a characteristics of load balancing, and this helps us in distributing the load somewhat equally amongst the base stations. So here are some of the key terms which I have color coded. So we'll go through them one by one. First of all, in the yellow color, we can see that in the denominator, I have a summation over xkj. Here, this term is nothing but the load at a single base station. So what I am doing is I am summing the throughputs, which are denoted by the Rij for each user I connected to base station j, and also normalizing them by dividing the load at a current base station. So this normalization, we can take it in terms of bandwidth normalization. For example, if the base station has a particular fixed amount of bandwidth resource, then by dividing with the total number of users attached to base station, I am assuming that I give each user equal amount of bandwidth share. So this is a normalization factor. So now moving on to the constraints, we find that there's an orange constraint first, which is to ensure that a user can be connected to a single base station. The second constraint in the blue is a relaxed association criteria. So here I would like to spend some time over this criteria. So generally, we know that a user can be associated to a single cell tower. So xij is a variable which states that if user I is associated to base station j, then that variable should hold the value 1, or else it will be 0. So here, in order to simplify the computation, I have relaxed the association constraint to be a real value instead of a binary, 0 or 1. So this helps in relaxing the computation. But while getting the result, for example, if I get this value of xij to be around 0.2, I can round it off to 0, or if it's 0.8, for example, I can round it off to 1, and I get an association matrix, which is not the actual value, but it's a close approximation to the actual results. So moving on, the third constraint in green is the pico base station load capacity constraint. Here you can see that there is a constraint on the j variable, which is for the base stations, and we have taken all the base stations set except the macro. So this means that for all the pico base stations, I'm checking that whether they are under their load capacity or not. This is an important constraint because the macro pico load factor is fixed from the beginning. So now moving on. Here are the results of the max-SNR scheme versus the load balancing scheme. Here you can see I have analyzed three metrics. First of all, system throughput in Mbps, system power consumption, and then the energy efficiency. Here we can see that the load balancing scheme does much better in terms of system throughput over the max-SNR based association scheme or our baseline scheme. And we have achieved a gain of over around 35% in the system throughput using the load balancing scheme than the max-SNR.
Hey, Mareesh, when you get an Xij that's like a half or 0.4,
yeah,
you're essentially at a half, or you just flipping a coin to choose one or the other?
Yeah, Professor.
And then what's the penalty you pay for that?
Professor, the penalty is that it's not an accurate answer. it's not the the ultimate best answer, but it's somewhat close. Because if it's 0.5, it means that I can either attach to the macro or the pico base station. But I have also have this constraint of the load capacity of pico. So if this constraint is not satisfied, then the user will automatically be attached to the macro. Does that answer your question?
So if you assign it and somehow then you violate this pico load factor constraint, you then cancel that assignment.
Yeah, Professor.
So somehow I guess I think, if you do the assignment and you don't violate this, then you get something that's maybe it doesn't meet what you think of as the solution to this optimization problem, right?
Yeah, Professor.
So do you just live with it?
Yeah.
Are the results and when you on the next slide that you kind of went to, the results take into account the loss that occasionally occurs when you have to do this?
Professor, I have not taken that into account because there is no such metric to quantify that. There can be a metric to quantify that, but the key point which I am trying to focus here is the improvement which I get over the system throughput over the max-SNR scheme. So there might be some error here in the results due to that normalization, but that wouldn't be such large value.
I guess somehow I heard the wrong answer. The answer I wasn't expecting to hear. The answer I was expecting to hear was that the performance results that you present simply reflect the small loss in performance. Is that right?
Yeah.
Like the fact that you don't get you're not just calculating what the optimization problems gives you with the non-binary assignment and claiming you get that.
No.
Okay. All right.
Yeah. Okay. Okay. And then I'll move on to the second or the third association algorithm now. So before moving on to the third association algorithm, I would like to have some background regarding the base station power consumption. So from the paper mentioned below, these four figures depict the base station power consumption model. So here on the macro cell figure, we can see that it shows a linear trend increasing from around 600 or 700 watts and going up to over 1000. And similarly for the micro, pico, and femtocell, we can see the graph. On the x-axis, we have the RF output power percentage. This can be taken as a load percentage. So for example, if the base station is 100% loaded, then the power consumption can be formed from this graph. So the two takeaway points from this slides can be, first one, this graph for the macro cells shows a linear increasing trend, and a similar trend can be observed for micro, pico, or femtocells. That is, all the small cells show a linear increasing trend. So we can model the power consumption for base station using a linear equation. And second, a point to note here is that the base station power consumption for the macro cell here is very large as compared to the pico cell. For example, 500, and here the pico cell goes at max to 16 or 17. So keeping these things in mind, I'll move on to the next slide, which depicts the base station power consumption model as a linear equation. So here is the slide which gives us the linear model for the power consumption. So here the variables used have also written the definition. The Pin is the base station power consumption. NTRX is the number of transceiver chains. P naught is a power consumption at minimum non-zero output power. We can consider this to be the intercept of a y equal to mx plus c kind of line. And the slope is given by del p. it's a load dependent slope for power consumption, and P out is the base station RF output power. So using this equation and the values of the variable according to my simulation model, the variables are having the following values. I'll use this table in the modeling and application of this power consumption model in the next slide. So here is the third user association algorithm, the power minimization based association algorithm. So here I will go around one line by line explaining each and every equation. So first of all, what I'm trying to do is maximize the negative of some term, which is same as minimize. So here inside this term, I have the linear equation, which I got from the previous slide. And also I have used the value of the load percentage of a base station. A load percentage meaning that how much percent of the load capacity is currently full for that base station. So using that and summing over all the base stations which I have in the system, I'll get a power, the total power of the system, and I'll then minimize it subject to some constraints. So here, these constraints, the first, second, and the fourth constraints are similar to the previous equations regarding load balancing. The only new constraint for this power minimization problem is a minimum data rate constraint. Here, Rij min is the minimum throughput supported by user I attached to the base station J. And this constraint basically means that I will first see whether an association would lead to the throughput for a user and a base station pair above a certain threshold value, which is Rij min. If it's the case, then attach the user to that particular base station. Here, this constraint is necessary because if I don't have this constraint, then all the users can be attached to the macro base station irrespective of the data. So these constraints help in reducing the load at the macro base station. Okay, then moving on. Here are the results of the power minimization algorithm in comparison to the max-SNR based baseline algorithm. In this result, we can see that for the system power consumption, we get a drastic improvement from 339 to 207, which is around 63% reduction in the system power consumption over the baseline algorithm. Also, we find that the energy efficiency metric is improved over the baseline algorithm. Now, moving on to the summary of the optimization metrics. So up till now, we have seen the baseline algorithm, the max-SNR based user association algorithm. Then we went and analyzed the load balancing based algorithm to balance the load as well as maximize the throughput. Then the third algorithm was regarding minimization of power consumption. So in order to summarize all the three algorithms for the maximization of throughput, what we want to do is maximize system throughput while load balancing and adhering to user association constraints. Similarly, for power minimization, we minimize the power consumption while satisfying QoS requirement for each user as well as the user association constraints. Here, the power constraints at the base stations are not included in this work because I am considering that each base station is currently transmitting at the full power. So now from the analysis and implementation of the optimization based load balancing as well as power minimization algorithm, we get an intuition that we can improve the system metric energy efficiency if we offload users from the macro cell to the small cell. So now keeping this intuition in mind, I'll move further in order to present the optimization that focuses on and maximizing the energy efficiency. So this slide shows the optimization equation that will maximize the energy efficiency. Here in this equation, the numerator term is the load balancing term, which we saw in the load balancing based algorithm. The denominator is the power minimization based term, which we saw in the power minimization algorithm. And the constraints are accumulation of all the constraints seen up till now. So this equation is the final optimization equation in order to maximize the energy efficiency of the system. So in order to solve this equation, now we'll see the next slide and see the different approaches that are possible and are presented in the existing works to tackle this issue. So this slide depicts an approach flowchart, which is kind of a way to see what are the different approaches that people have taken or the existing researchers have shown. So first of all, for any optimization problem, which is similar to that presented in the previous slide, there's a mathematical approach which people tend to follow by relaxing some of the constraint, proving its convexity, and then solving it. This solution can be, again, based on distributed approach or a centralized approach. For centralized approach, interior point polynomial time methods come up a lot of time, like as the a strong solution for a centralized approach. And for the distributed approach, many authors mention primal dual distributed algorithm. But these algorithms are a bit too complex at this stage for me to analyze and then implement them. So I took a different route, which is a non-mathematical approach and a heuristic-based algorithm. Another key point to note here is that in the non-mathematical and the heuristic-based approach, this approach, since it doesn't involve any mathematical computation or solving of the convex optimization problem, so this is potentially faster than the previous solutions when our network scales with a large number of users or if there are mobile users. So keeping this in mind and now proceeding with the heuristic-based algorithm, I now present the user association algorithm, which I have designed called E-ASSOC. So here is a brief overview of the algorithm. But in order to understand the functioning of the algorithm, let's move on to the next slide, which is the flowchart. So here I would like to explain both of the flowcharts mentioned in the slide. So for the left flowchart, we start and we check whether a user is getting the best SNR from a pico base station and the second best SNR from a macro base station. If this is the case, then what we do is we check if the current load for that particular pico base station is less than the maximum load for the pico base station, then we attach the user to the pico base station because the user is already getting the best signal from that pico base station. But if it's not the case and the user is getting the best signal, but the load capacity of that pico base station is full, then we attach the user to the macro base station. Then moving on to the next flow chart, here we have the condition that the best SNR a user receives is from a macro base station, whereas the second best SNR received by the user is from a pico base station. If this is the case, then we check whether the difference between those two SNR values is less than a particular threshold, predefined particular threshold. If that's the case, then we further check if that pico base station is not fully loaded, and if it's true, then we attach the user to that particular pico base station. But if the threshold difference condition is not satisfied, which means that the best and the second best SNR a user receives is greater than the difference is greater than the threshold, then we attach the user to the macro base station so that the user doesn't get impaired. And similarly, if the load capacity of the pico base station is full, then we attach the user to the macro base station. So until now, does anybody has any question?
You choose the threshold of 30.
Yeah, Professor. Yeah. Okay, then moving on. So,
Question, Mareesh.
yeah, Professor.
How did you choose the threshold of 30?
Yeah, Professor, I'll explain. So by choosing the value of threshold, I wanted to choose such a value that the system throughput is somewhat closer to that given by the load balancing and the power minimization. So like 30 dB gave me the result which is closer to those values so that I can somewhat analyze them on the same page. So that was the reason behind selecting the 30 dB threshold. And also like the algorithm which I mentioned below, before slide. So here the value 30 is the same as what I have used for my analysis. So from our previous slides, we have seen that the max-SNR or the baseline algorithm, then in comparison to that, the load balancing and the power minimization algorithm. Now we see our designed E-ASSOC algorithm. So here, while comparing all the algorithms, we can see that the power minimization algorithm has the least power consumption amongst all the algorithms. The energy efficiency metric has been improved over the baseline max-SNR algorithm by all the three algorithms. And in particular, the E-ASSOC algorithm shows a gain of 41% in system throughput over the baseline scheme and a reduction of 32% in the system power consumption over the baseline. So here we can see that the results shown by E-ASSOC over the baseline scheme are show an improvement over the energy efficiency. Now, why these improvements are coming? So a clear picture can be seen from my next slide, which is this. So this slide is very important because it shows the average number of average load or the number of users that have been attached after the implementation of each and every algorithm. So here the number 1, 2, 3, 4, and 5 represent the base stations, and specifically 1 represents the macro base station, and these 4 are the pico base stations. So for the blue scheme, which is the nothing but the baseline max-SNR scheme, we find that most of the users, almost all the users have been attached to the macro base station because of its strong signal to noise ratio for each user. This scenario is means for the same max-SNR scheme, we can see that the pico base station have very few number of users. But if we see the same plot for load balancing and power minimization scheme, we can see that the height of the graph for each and every base station is somewhat similar. This means that the load balancing is working, and load balancing in terms of number of users is shifting the users, all the users that were previously in the max-SNR scheme attached to the macro, now distributed over the pico cell. Similar results can be seen from power minimization also with the E-ASSOC scheme. So that's the main reason why E-ASSOC scheme is able to perform better than the max-SNR scheme, due to the distribution of users from the macro cell to the small cells, which was also our intuition from the previous slide. Now, moving on, here is the CDF plot for the number of users versus the average throughput in Mbps for all the different schemes. So from this plot, we can see that the max-SNR scheme has a wide range, means there are very few users which are having low throughput. Also, there are very few users that are having very high throughput. But for the other three schemes, which have a load balancing features inbuilt in them, we find that the distribution is not that much wide. For example, they start around 12 and maybe go around 16 or 18. So this further solidifies the results from our previous slide, stating that the distribution is much more uniform in terms of load, which is the number of users. A further investigation shows that these mean user throughput obtained from the previous CDF graph for each and every algorithm shows that the load balancing, the power minimization, as well as the E-ASSOC have a gain over the max-SNR scheme. And in order to evaluate the fairness of each scheme, because we don't want a scheme just to increase the throughput, whereas decreasing in fairness. For example, if the algorithm provides all the bandwidth to the user, which is getting the best signal. So that wouldn't be fair to all the other users in the system. So in order to analyze such a fairness metric, I am using here the Jain's fairness index, which I have depicted by the equation on the left-hand side. So if we compute the Jain's fairness index for all these algorithms, we get a value which is shown in this table. So from here, we can see that the max-SNR algorithm has a Jain's fairness index of around 0.9, whereas that for the other three algorithms is much higher. So here I would like to point out that the Jain's fairness index, if its value is 1, it means that the system is fair. And the system is fair in this sense that all the users are getting equal amount of the resources. So thus we can see that in fairness terms also, the E-ASSOC algorithm is improved over the max-SNR based algorithm. So now moving on. This is the conclusion slide, and here I would like to present the summary of the results that I have obtained up till now. So first of all, implementation of MATLAB-based simulator for heterogeneous networks. The second important result that came out from this work is the load balancing, implementation of load balancing scheme and the improvements over max-SNR scheme. Then the third point is the power minimization scheme and its improvement. The fourth point is the E-ASSOC user association algorithm and its improvement over the max-SNR scheme in both in terms of the system throughput as a power consumption. And finally, its improvement in the energy efficiency terms over the max-SNR. So at this point, I would like to ask the audience if they have any questions up till now, and I'll be happy to answer them, or else I'll move on. Okay, so if there are no questions, I can move on. So here is the future work that I want to do to further improve the work. For example, the first point is mobile users. I want to implement and evaluate the results of all the schemes in terms of mobile users taking interference into account, because this was not taken in this work currently. Then first of all, reading and then applying linear fractional programming in order to take the mathematical approach for solving the optimization problem. And the third point is evaluation of the performance of the user association algorithm for the latest and the upcoming 5G standards. These are some of my references. I've tried to categorize them in terms of keywords and specific sections they cater to. CGPP specs, heterogeneous networks. And these are some more references. And that's it from my side. And